In this video, we'll be talking about another application of operational amplifier, and that's this operational amplifier can be used as a differential amplifier, or we may also call it difference amplifier. So differential amplifier. So how we can do that? We have an operational amplifier, okay, and we have its inverting terminal, we have its non-inverting terminal, then we have an input resistance, say this is Rx, and we have the output, and then we have the feedback resistance, that is say Ry, and then we have another resistance here, and the magnitude of this resistance is same as that of the magnitude of this resistance, so this is also Rx, and here this resistance is same as that of this resistance, that's Ry, and this is grounded. So here we give an input, say for example V1, here we give another input, say V2, and what's clear about this diagram is that we can immediately talk about the output here. So what will be the output? Output will be proportional to the difference of V1 and V2. And this is what we have to achieve by analyzing this circuit, so that we can say that the circuit that's out here can be used as a differential amplifier, where it means that anytime you make use of a circuit in this fashion, you are going to amplify the difference of the voltages between the two inputs of this operational amplifier. That should be the case. So in order to start with this concept, if I choose on here, I mean here this point as a junction P, and this point as a junction Q. This is how it is. So let me start from here. So this is V1, this is V2, and suppose the voltage that I have here is VP, and the voltage that's here is VQ. Okay, that's the point. So if I start with KCL, Kirchhoff's current law at junction P. Okay, if I start with that, for that I have to write down the currents. Let us assume this current is I1, and here I have the current, say for example here I have I2, okay, and here I can't have anything because whatever is here is understood that its value is going to be 0, because the input impedance of the operational amplifier is large. So so let me choose it as I3 here, because there should not be any confusion. This is I3, and then here okay, let this be I3, and then here we'll talk about the currents at this junction later on. So moving on here, using KCL at point P, I'll get I1 equal to I2 plus I3. So we know that this I3 is 0 because the input impedance is extremely large. So this I1 is going to be equal to I2. So we can write down this equation in terms of voltages and current and resistances. And for that, what is I1 is it should be V1 minus Vp divided by Rx, and this should be equal to I2. What's the voltage here? Say this is Vp minus what is here? It is 0. Choosing here 0 divide by, this is Ry here. Okay, so this is Ry. So this is my equation right now. So let me go to another page and see what happens. So this is like getting now if I go back to this circuit, it's clear that this Vp Vp, I can boil down this like this. This is V1 by Rx minus Vp by Rx is equal to Vp by Ry. This is the case, right? So from here we can proceed. So what's going to happen here is, what is V1 by Rx is Vp by Ry plus Vp by Ry. Okay, so V1 by Rx is Vp times 1 by Ry plus 1 by this is Rx, 1 by Rx plus 1 by Ry. So we have been evaluating it like this, and we can see here what's going on is we have chosen this junction, right? And we want to proceed from here, and we have to use we have got V1 from here. So if I go on like this, so what's going to happen here, if I want to find V1, it must be Vp. Okay, Vp, V1 by Rx, keep it like this. So this is Rx plus Ry divide by Rx and Ry. So I can close it from here, right? So this is my Vp. I want to calculate this Vp. So this Vp must be V1 by Rx times Rx Ry upon Rx plus Ry. So we can cancel these Rx's, and we will find Vp equal to V1 times Ry divided by Rx plus Ry. Now we can call it, say for example, I'll call it as equation 1. Now let's go back to this slide and see. I want to do the same analysis at the point Q, right? So here I'm using KCL at the junction. So Q is a junction, so junction Q. What's going to happen is, so we have to write down some currents here. So we have here I3. Say this is I4, and this is I5, and this is, say, so I think this should be let us take this as I6. And this may confuse us with this R4. So, or I should call it, okay, I6 is fine. So this is here I4. Okay, so here you have the current coming and going, and you can use KCL, and KCL will give us what? It will give us I6 equals uh, it equals what? It equals I4 plus I5. But immediately I will say that I5 is 0 because the input impedance is very large. So I have I6 equal to I4. So that should be the case till now, right? And how should be the equation written here? It should be, yeah, instead of I6, it is V2 minus VQ by Rx, right? Equals, what is I4? I4 is VQ minus, it's VQ minus V out, divide by R4 or Y. Oh, that's not 4. I have written it badly. This is RY. Okay. Anyway, whatever is done is done, and we have achieved some result here. Now, here is another important point, that instead of this VQ, I can use VP under virtual ground condition. So, virtual ground condition, we understand that we have already discussed about that. So virtual ground, in that case, I can replace VQ by VP. So if I do that, I will get this equation as V2 minus VP divided by Rx is equal to VP minus V out by RY. And we will do the similar analysis here, and using the similar analysis that we'll be doing, we'll be able to to reach to an equation. Say, let's have this 3. Now what's going to happen is we have this equation. What's that? That is V2 minus VP divide by Rx equals V2 minus V out divide by Ry. Now this is the equation, and we will do the same analysis that we have done in the previous case, and we will achieve a result like this: V out by, you can do this simple mathematics over here, divide by Ry is equal to VQ. But we understand it's not Q, it's P. Okay, times Rx plus Ry divide by Rx or Y, then minus V2 by Rx. This result we will obtain when we will evaluate this equation. Very simple. And this this I will call as my equation second. And if I go rightly back to the previous page, I have this as equation 1. So instead of VP, I can use this. Here it is 1. Okay, I have a bad handwriting. So here I can write, instead of this VP, I can write this equation. So I will substitute what 1 in 2. So in doing that, what am I going to get is V out by Ry equals, so what is this? This is this is V1 times Ry by Rx plus Ry, Ry by Rx plus Ry. I'll close it. Then I have the original bracket here. This is Rx plus Ry divide by Rx Ry. Here I have minus V2 by R2. All right, any cancellations? I think these two will cancel. Now I will take this Ry. I think this Ry and Ry will cancel. So this V out will be Let us take this Ry up now. It will be V1 times Ry divided by Rx minus this Ry will be multiplied to this. So this is yeah, here it is Rx. Okay, I'm sorry, I have committed a mistake. It's Rx. Here it is Rx. Okay, so so in the original equation, it has to be what I have written here. It has to be Rx. Okay, so here, what am I going to get is minus V2 times Ry by Rx. And final equation is V out is Ry by Rx times V1 minus V2. So we can see here that the output that we are obtaining from this circuit is basically the difference of the two inputs that we have subjected to the operational amplifier. So it's the difference of these two inputs. And in addition, we have this proportionality constant, that's Ry by Rx, and this certainly gives us the measure of the gain that the amplifier has performed. So we can see here that the output is the subtraction of the input functions. So this is why we call it as a differential amplifier or difference amplifier.